Okay, so in this video, I'll cover the thing that you have to derive the Hamiltonian equation, okay, from the variational principle. If you can remember what is a variation principle, variation principle says that when a system is evolving in the time and the system is following the correct path, for the correct path, the action that is your integral from the t1 to t2 l dt, this action should have to be should have some stationary value. That means your delta, even if a s equals to your t1 to t2 your l dt, this is action. So for the correct path, your delta s equals to 0. That means your delta s equals to your t1 to t2 delta l dt, that equals to 0 for the correct correct path. Okay, for the correct path. Now, what is a Hamiltonian? Hamiltonian equals to q dot p minus h, sorry, minus l. So what is a l? L is equal to q dot p minus h. H is a function of q p t. So in general, you can write, if you're writing down the Lagrangian as a q dot p minus a, so your in general the Lagrangian would be a function of q dot p and t, and also considering the p dot. I know that there will be no p dot, but I'm just considering the p dots so that uh, it will help you in a calculation. Okay, I mean, this can help you in visualizing the formulation of the Hamiltonian from the variation principle. That's all. Okay, so start it. So this is a, let's say this is a correct path, and if you have done this variational principle, and if you have derived the Lagrangian formulation, you know that for the correct path and for a varied path, which kind of varied path? This is a slightly varied path, and this is for the correct path. We are writing down q t, and for the varied path we write down q as a alpha comma t. And for this calculation, we are taking that age is nothing but q dot p minus l. I'm considering one generalized coordinate and one your generalized momentum. Okay, so that you can get the calculation easily. So age is this, and q for the slightly varied path, this is a q of alpha t is equal to, for q for the actual path, okay, plus alpha times some eta of t. Okay, alpha times eta of t. Okay, and your p for the varied path is equal to your p of 0 comma t for the actual path plus, let's say, alpha times some eta prime t. Okay, so her eta and eta prime are the, eta and eta prime are the well-behaved function. They are continuous function, and they are 0, eta of t1 and eta of t2 equals to 0. T1 and t2 are the two endpoints. One is a t1 and is a t2. Two endpoints. The system is evolving from here to here in the phase space, and we are considering the first point is t1 and second point time is t2 and first point time is t1. In this both ends, the eta will be equals to 0, and in between them this eta is totally well behaved. This is a continuous function, and its first derivative and second derivative is also continuous, and eta prime has the same kind of nature, and alpha is a non-negative, okay, real, and your very infinite small in quantity. Okay, real positive infinite small quantity is alpha. That is defining the variation from the actual path. Okay, if we have done the variational principle, you know it is very well, very much in details. Okay, so this is thing. So your delta s is what now, is your t1 to t2 delta L. L is a function of q dot p dot and time t. times dt. From here you can write down that delta q equals to q of alpha t minus q of 0 comma t. This is equal to alpha times eta of t, and from here you can write down the delta of q dot, that is equals to alpha of eta dot of time t, and delta of p you can write down alpha of eta prime t, and your delta of p dot you can also write down the alpha times eta prime dot t. Basically delta q is equal to q minus q0, and delta p is equal to p minus p0 basically. Okay, and time derivative will be in the same way, the p dot in the same way this p dot equals to uh, p dot of t minus alpha times eta dot of t, because alpha is constant here. Okay, infinite is a small value. Okay, so your delta is equals to here t1 to t2 del l by delta q plus del l by delta q dot plus del L by delta p plus del L by delta p dot, okay, and the whole thing dt. If you put the value, so del L by delta q, okay, alpha times eta of t plus del L by del q dot, and delta q dot is your alpha times eta dot of t, okay, times dt plus t1 to t2 del L by delta p alpha times eta prime of t plus del L by del p dot alpha times uh, eta prime dot t dt. They're both the same kind of equation, right? I'm just solving this part. Okay, I'm solving this part. Okay, you have to solve this by parts. From t1 to t2, I'm just solving this del L by del q dot alpha times eta dot t dt. That will give you del L by del q dot, and alpha will be outside, and eta dot integration, that will be eta dot of t from the t1 to t2 minus alpha times ddt of del L by del q dot times eta of t integration t1 to t2 and your dt. Okay, okay, and if you put this value here, that will becomes to t1 to tt your del L by del q minus ddt of del L by del q dot, okay, alpha times eta of t dt, and in the same way you will also get here del L by del p minus ddt of del L by del p dot into alpha times alpha prime of t and alpha of t and dt. Why? Because this term will be 0, right? This term will be 0 because eta of t2 and eta of t1 is 0. At the endpoint set to 0, so this part will be 0. In the same way, here you will also get something del L by del p dot eta prime t, and that will be also become 0 at the two endpoint, this thing, integral value. Okay, so you will get something like that. And as we have chosen the actual path, this is your delta s. For actual path, delta s equals to 0. So this term will be equals to 0. Now your eta prime t is arbitrary function, is arbitrary continuous well-behaved function, that is a first and second derivative is continuous. That's a function. The eta prime is also some arbitrary function. Okay, so if this whole thing is 0, we can easily write down this part is 0 and this part is 0. There is a uh, fundamental lemma. You can go to the question where they have derived the Lagrangian equation from the variation principle. They have mentioned it. You can say that there is a m, there is a eta times dt. Okay, so eta is a continuous function. Okay, an arbitrary function. If that is equals to 0, then your m will be equals to 0. So that's what I have used here. It's a fundamental lemma. You can easily search or say look for it in the book. So your del L by del Q is equal to, or del L by del Q minus ddt of del L by del Q dot equals to 0, and this is nothing but your Lagrange equation. So you have also got the Lagrange equation here, and the second part, your del L by del P minus ddt or del L by del P dot equals to 0. So you got the two equation. Now, okay. Now what is the L? L is equal to Q dot P minus H, right? So what is your del L by del Q? Del L by del Q is minus del H by del Q. So del L by del Q is to minus del H by del Q. I'm putting a value of this minus ddt, and del L by del Q dot is what? P equals to 0. So P dot equals to minus del H by del Q. Okay, and look into here. Del L by del P. If you do the del L by del P, you get the Q dot minus del H by del P minus del L by del P dot. There is no P dot term. I have said that there is no P dot term. But we are taking this so that we can take some similar term both, so we can visualize it. Okay. And what about there is some P dot in the L? That's the reason why I have considered the P dot in the first line. So, so as there is no P dot, so that particular 0 equals to 0. So you'll get some Q dot is equal to del H by del P. You got it right. So you got the Q dot equals to del H by del P. You got the P dot equals to minus del H by del Q. So I have considered here only one coordinate. I mean one generalized coordinate, one momentum. If I go for the whole system, there is a twin coordinate. I mean in generalized coordinate and generalized momentum, then you got the pi dot is equal to minus del H by del Qi, and you got the Qi dot equals to del H by del Pi. And these are the Hamilton's equation of motion, and you are getting this from the variation principle. That's all.